the information. Welcome members back to our mathematics. Today I have a slight problem with electricity, but I think we'll have somewhere. We want to look at our lesson 33. So I'll be looking at something we already know, which is fast powering algorithm. And we saw how important it is in our calculations, especially making calculations easier for us or making them faster, so that even if you were to working is faster. The other name for the fast powering algorithm is some books refer to it as exponentiation by squaring algorithm. This terminology just means fast powering algorithm. And we've said that it's very efficient in computing large powers, especially modular arithmetic. We have large powers, and then this would be a faster way of doing that. Some texts also call it square and multiply algorithm. So it has several names depending on the text you are using. So it's either fast powering algorithm, or it's the exponentiation by squaring algorithm, or square and multiply algorithm. So I've said that it reduces the number of multiplications needed compared to if you had to do it manual straight using multiplication. The electricity has just come. Let me connect this laptop so that we are not proceed without interruption. Okay, so why do we require this method? I've said the reason we require it is that in some crypto systems, as we had already seen and we will see again, like RSA and other crypto systems, we have several crypto systems. RSA is one of them. We are required to compute large powers in such crypto systems. So, and computing large powers may take a long time if we are not using fast powering algorithm. So that is why then we require this fast powering algorithm, so that as we proceed with these crypto systems, we already have this, and that will be an advantage to us. Now, the algorithm is already here. Let me just show you the algorithm. What we have, supposing I have a number. Let me say the number is a raised to k, the way I have it here. So the way I want to approach it is I want, first of all, to write this k as in binary, base 2, to write it as base 2, this k. Then after writing it a base 2, you know that we'll be using numbers 0 and 1. We already did this, changing bases. Now after that, we'll then go straight to finding out what a raised to k is. But of course, we will have to square the s. We shall get a raised to 1, a raised to 2, a raised to, you square the one just above. So this will be a raised to 4, then a raised to 8, and so on. But what will be guiding us is the k here, written as base 2. binary number. So that will guide us how many times we are going to square this. So I'll just show you an example we had already done. Then we go to the code. This is just the explanation of what we are doing, what the algorithm is doing. If you have A, you square it, then you square the one just above to get A raised to 4, then you square the above to get A raised to 8. And so supposing this was giving you A naught mod M, then when you square this to get the next line, you'll be squaring to get A naught square. So let's call this A naught square to be A1. Then when you square this, so you're squaring A1, this is what you get, and I want to call it A2, and so on. So that is what the algorithm is talking about. You look at the algorithm. I just want to show you the example. Example is 7 raised to 35. These are small number, but we'll be looking at bigger numbers, especially when you begin using the code. 7 raised to 35 mod 27. So as I said, first of all, I convert this 35 to binary. So when you convert 35 to binary, this is base 10. What you get is what I've written here is 1, get 0, then there's a 0, then there is another 0, then there's a 1, then there's a 1. So this number in base 2 is supposed to be that. So what I've just done, I've expanded it. So when you expand this number, base 2, when you were writing, when you are changing from bases, from one base to another base, if you are given base 2 and you want to change it to base 10, this is base 10. How do you change it? This is how you change it. This is how you change it. What do? You take the first number here, this 1 multiplied by 2 raised to 0, then this other 1 multiplied by 2 raised to 1. So it's from here is 0, 1, 2, and so on. As those are the place values. The place values, there's 0, this powers 0, 1, 2. Those are the place values. So this is a binary number. To convert it back, that is how you do. You take this 1 times 2 raised to 0, then this 1 times 2 raised to 1, then this 0 times 2 raised to 2, this 0 times 2 raised to 3, this 0 times 2 raised to 4, this 1 times 2 raised. So that is how you. So that's what I wrote. For me to have written this, first of all, I converted that 5 to. Of course, this conversion is not necessary. I was just showing you that this number is the same number. The only thing I require is write this number as binary. Then you know that you'll have to square how many times? 1, 2, 3, 4, 5, 6. So you can see I've squared 6 times. 1, 2, 3, 4, 5, 6. Then again, this binary number will tell you what you will combine. After squaring that, it's telling me that I'll combine this first one, combine the second one, then these ones will give me 0, then combine this other one. So that is what it's telling me. So that it means, you see, this is the first one. This corresponds to that one. This other one, no, you begin from which side? This 1, 2, 3. You begin from this is the first one. This one is the one which corresponds to that. Then this one corresponds to the next, the next one, then and so on. And then this one corresponds to that, and so on. So it means the ones we shall combine are the only ones, the only ones with ones. The ones with the 0, there's no need. Of course, what is happening is what I've written here. What is happening is what I've written here. I've taken this 7, then raise it to this 1. Raise it to that 1, then times I've taken this 22. Okay, I said this, the first one is corresponds to the, we begin from the right side, going this way. Begin from the right side. So this 7 times raised to this 1. And then there is 22, this 22 raised to the next 1. Then times there's 25 raised to the next digit, which is 0. Then times 4 raised to the next digit, which is again 0. Then there is 16 raised to the next digit, which is again 0. And then there is 13 raised to the last digit, which is 1. So whatever is raised to 0 is just 1. Any number raised to 0 is 1. So what that means, this is 7 raised to 1. Then this is 22 raised to 1. Then this is 25 raised to 0, which is 1. You can ignore it. Anything multiplied by 1 is 1. Again, this gives us 1. 4 raised to 0 will be 1. Again, 16 raised to 0 will be 1. And then 13 raised to 1 will be 13. So finally, we just have 7 times 22 times 13, and that's what I have. So what I said, this will then guide you. This one guides which ones to combine. So for instance, you will just have omitted the ones you have zeros and just included the first, and these other two. And remember, the one that is raised to 1 is the one on the far right. And then this other one, the next one, then we begin from the right side going to the left side. Okay, so we had done this one earlier, although in class I used a different approach. The two approaches are the same. They give us the same result. Okay, just another example just to illustrate that again. And then we go to the code. I take the power, and this power, write it in binary, and this is what I get. Of course, we have a code. We have a code for writing, changing a number from decimal to binary. We already have that code. So if the number is too huge, again, we have that code to assist us write it in binary. Now, so 27 raised to 1, then 27 raised to 2, and this is what you get when you raise them, when you raise that. So you're just squaring the number just above. So 27 is square. Then you reduce it mod 313. And then I don't know whether there could be people who don't know what we are doing. I'm explaining because we done this one earlier. So if you have a calculator, just supposing you don't know what we are doing, I'm taking 27 raised to 1. 27 raised to 1. This number is smaller than 313, so I just write it as 27. Then square it with the next one, 27 times 27. The answer that you get, divide by 313, and then write the remainder. So this is the remainder. So the answer that you get here, divided by 313, the remainder is what you write. When 313 goes here, what is the remainder? So the remainder is what you write here. And then, again, square the one just above. So this time I'm squaring this part to get the next part. So when you square 103, so 103 times 103, the answer that you get, again, mod 313, it means divided by 313, then write for us the remainder. So you do the same thing, even to get this 150, again, multiply 280 twice, 280 twice. And so when you write the code will just be doing exactly this. And then divide this by 313, and then give us the remainder. So giving us the remainder every time. Again, square the one just above until you reach here. Then once you reach here, which ones are you combining? We go back here, and you can see that we are combining the ones that have ones. Only the ones that have ones, the ones that have ones. So in this case, this 27 corresponds to this 0. So we are not interested in that. But 103 here corresponds to the next one. So 103 is required. And then 280 corresponds to this 0. So we don't require it. And then 150 corresponds to this 1. So we require it. So we only multiply the ones which corresponds to 1 when you convert the power to binary. So those are the ones we are interested in. Of course, you know what has happened to the rest. What has happened to the rest is that when I took this 27 and raised it to that 0, I got a 1. So again, but for this other one, when I took this 103 and raised to 1, I got 103. So 103, that's why I have it here. These other ones will give me 1, 1, 1, 1. When I multiply, 1 has no effect. Now, so when I multiply all these numbers, the ones you are seeing here, and then divide by 313, the remainder is what I write, is 1. The remainder is 1, and that is what gives us what we wanted. What we wanted was 27 raised to this mod 313. So the answer is 1. Okay. Supposing that there's anybody who has not understood the explanation, maybe when we meet on Thursday, we will again try to explain. The Rust code is here. The Rust code, so main function is just giving us the base. For this case, what is the base? 27. And let base equal 27. What about the power? Let exponent is the power, and then modulus 313. Let modulus be 313. And then let result. So the result will give us the base, the exponent, and the modulus. The result of that, the result of the base, this base, the result of this base, this exponent, and this modulus is what we are calling for here. So we are calling for the result mod exponent. Then inside here we give our 3 parameters. Our 3 parameters that we defined. These are the parameters. Then it will print what you, this equation, it just prints this equation. It prints 27 raised to 13. So this is the exponent. The exponent is here, the base is here, then the mod, which is 313, equals, and then it gives you the result here. So again, we have our brackets here, our curly brackets. The first one is the base, the second one is the exponent, and then the third one is the mod, and then the result. Now let's go to how it functions, how this will be functioning, and again I'll run that, how it will be working. Now you input, this is a mutable base. Mutable base, it means the base will be changing, and I'm showing you how the base will be changing from time to time. And this base is a U64. Of course, you can change 64 to 128. But if the number is too big, if the numbers are too big than what U128 can accommodate, then you can import libraries like big for the libraries for big integers. Libraries for big integers, and again I'll show you. I think I have a code that I have for big integers. This you can this are 64-bit, 64-bit. And again, we are interested with the positive values only. That is why you can see I've used U and not I. I've not used I. Because every time you get a number, positive number, for instance, and then you raise it to a positive integer, I expect that the result will be positive. And so that is why I've used U64 and not I. I, we said we are using I if you expecting also some negative results. So our base is mutable, to be changing. It's not static, be changing. If the base is 6, we expect that next time it changes to another figure, and so on, and therefore it's mutable. The exponent will also be mutable. I'll show you an example. The exponent will be changing. The modulus is not mutable. So the modulus is not mutable. And then the result will be mutable. And again, U64. You may want to change that to 32 if you want, so to deal with the smaller numbers, or you want 28 if you want to deal with the larger numbers, or you want to change it to libraries that deal with the very big integers. Now look at what it says here. It begins that if the modulus is 1, then it prints 0. Prints 0, gives you 0 as the result. Because what we are saying is this. Suppose you have any number, 27, for instance, raised to 234, and then the modulus is 1. So you're asking ourselves, if 1 were to go here, in fact, what this one is just saying is, what is the remainder if this modulus goes here? So if the modulus is 1 and it goes to any number, we expect that the remainder will be 0. That's what it's saying. That's what it's saying, that if the modulus is 1, then automatically it gives you 0 as the result, because any number, 1 goes into that number and the remainder will be 0. Now, if that is not the case, if the modulus is not 1, then we begin here and we say we let the result be mutable. We let the result be mutable and initialize this result as 1. That's the initialize. We initialize. We let the result be 1. Now, that is if the case where the modulus is not 1. If the modulus is not 1, then the program lets the result be 1, and that will be mutable, so it will be changing. Then the base we said it changes. So the base becomes the current base. Or you know what this means? You know what this means? We've already talked about that. Whenever we talk with this, whenever we write A and then this sign B, this means the remainder on dividing B, A by B. The remainder on dividing A by B. So that means, for instance, if I write 4 and then write 3, the answer is 1. So it means 4 divided by 3, the remainder is, so this is the remainder. So we are saying the new base we said will be mutable. At this point, we say the base will be mutable here. So the base will be mutable. So we begin with the base, which is 27. The base is 27. We begin with the 27. Then the new base, therefore, the case where the modulus is not 1, and the result, we will say let the result be 1. The new base becomes what remains on dividing the old base by the modulus. by the modulus, what remains. So that is what the program will be doing. So the program does that. And after doing that, it enters a loop. It enters a loop, while loop. The while loop here is very important. You see, these are the first two things it does. The first thing it does, it lets the result be mutable and it gives it initial value of 1. So it will be changing 1, goes to another value, goes to another value, and so on. Then the base changes the base. The base is again immutable. The new base becomes the old base, dividing by modulus. The remainder of that is the new base. Now, the while loop has a condition. The condition is if the exponent is greater than 0. If it's true, then we go inside. If it's not true, it means we exit the loop. So the loop we will not have anything to do here. If the exponent is greater than 0, that's when we enter the loop. For instance, our case, the exponent is 234, so it's greater than 0. So it's greater than 0. That means we now enter the loop. So when we enter the loop, we meet the first thing is the if condition. And this if, again, there's something to consider here. If the exponent is odd, this is what it means. If the exponent is odd, and I think you have seen why I'm saying that, because what I'm saying is the remainder. I'm saying that the exponent on division by 2, the remainder is 1. So if the exponent on division by 2, the remainder is 1, it means this exponent is odd. That's why I'm saying that if the exponent is odd, then the result, we had already initialized the result to be 1. Now, when we enter this loop, the result now becomes the old result times the base, and remember the base, we are getting it from here. We're getting it from here. So the old result times the base, this answer divided by modulus, you just write the remainder. Just write the remainder. So the result will be the remainder of this. The result will be the remainder of this. Now, what about the exponent? The exponent now, again, is mutable. The exponent is mutable here. The exponent is mutable. You say the base is mutable. So the base, this is how the program calculates the base. The base changes. So this is how the program calculates the base. The new base is the old base divided by modulus, the remainder of that. There is the result. This is how the program will be calculating the result. This is how the program will be calculating the result. I'll show an example. This is how it will be calculating the result. And then how it will be calculating the exponent. The exponent will be mutable. So this means the exponent is the old exponent divided by 2. And this one, we are doing it bitwise. So you calculate dividing the exponent by 2 bitwise. Then again, look at the base. Now, there are 2 ways you're calculating the base. The first way was just when we were beginning. But once we enter this loop, the base now becomes the base times base divided by modulus, the remainder of that. So you square the base, then divide by the modulus, the remainder of that. Then the result. Now, so this loop, when do you exit the loop? So this process that I've been explaining here continues, and I'll show you an example. This process continues until this point is not satisfied. Until this point says, if the exponent is greater than 0, we enter the loop. So once we continue this process until the exponent is not greater than 0. So when we find the exponent to be 0, we exit the loop. the exponent must become 0. Then you exit the loop. So when you exit the loop, you come here and read the result. This is why we read the result. Now let me just show you the how it runs, and then I show an example of how this program is calculating that. And it's just the same thing. It's just the same thing we've done in the first two examples, but now I'll be using the language of the program so that we understand that the two are the same, only implemented differently. Okay, this one I was explaining how the code works. So let me just open, let me go to where my program is. And I told you that we can deal with bigger integers and even smaller integers. But when you're dealing with the bigger integers, for instance, I'll show you how you do that. I'll just show you how to do that, how to modify the code we already have to have a code that will now accept bigger integers. It's just the same way, for instance, when you want to change from U64 to, let me say, U128. That's the same we're doing this time, but we'll be using a library that accepts bigger integers. But it's just the same thing, just change the code and then it will just work. So I just want to stop sharing this so that I can now share the code. You can see it. Eh?
Yes.
You can see the integer that begins with 6666.
Yes.
That is my base. And the exponent is also bigger. And then I have modulus here. But we will try and have them bigger than this and see whether it will still work. And if it doesn't, then we look for the library. Now, so you can change this U64 to 128 if you want larger numbers again. But there's an extent where 128 will work and some point it will not work. Now, it's just a very short code, it's just a very short code. So the code is. Okay, so let's run. It has printed and says this number raised to this number, mod that. The result is 157, 65, 385. When you run it, that's what we get. Let's raise these numbers. Let's just make them bigger a bit and see whether it will still accept. In fact, the more we can maintain it or change. Let's try to run this. Okay, it does not. And what does it say? It says that error, literal out of range of U64. So this is out of range, is bigger than U64. Of course, what I'm saying here is what is out of range is this base. Let me reduce it a bit and see. Let me reduce a bit and see whether it will be in the range. Okay, let's again run. Okay, this is still outside. Still outside. there's no need of using, because we will be having this number. So when you have, if that is the number we have, we don't need to reduce. Let's just change this to 128. 164, change it to 128. No, this 64, change it to 128. Wherever it appears, so we want to see whether it will work. Whatever it is, whatever it appears, let's change it to 128. So, which means 128 bits. 128 bits. Expect that this will work. We've changed it there. So let's just again run this. Because if that is the number we have, then we cannot reduce it. It has worked. It has run this num. It has given us the result. So it means the code is okay. You can see the number is a bit bigger. Let's again increase this number and see if 128 will still hold it. If 128 will still hold the result. If it doesn't, we go to the library that uses the bigger numbers. Yes, 128 can run this. We increase a bit and see whether it will run. Oh, 128 will not run this. Now let me just show you the one that the code for. So the only place that I'll be changing is this, and I change with the library. Of course, import the library there. So the only changes will be there. So you'll see that there are not much things that you do when you're changing that. Yeah, you don't do a lot of things just to change. Where there's 128, you just change that with the library. Just a minute. You can see the one I'm sharing now. Are you able to see it? Yes, so you can see this point. These are the libraries. This one deals with the big integers. And then we have there are three libraries here. Of course, before I forget, let me show you the cargo atomil. It has, again, those dependencies for the big integer and those traits, number traits. You are seeing that, huh?
Yeah.
What I'm sharing under the cargo atomil.
Yeah.
Okay, so you can see the only change I've done where there was 128, you see this, I will have written 128 here. I will have written 128 here to mean that I want this number to be 128 bit. I will also have written 128 here to mean I want it to be 128 bit. I will also have written 128 here to mean I want it to be 128 bit. But now I've written big unit. And this one I've also written big unit, this one the same. And again, at this point, the base, I will have written the base to be 128. I will have written the exponent to be 128. I will have written the modulus to be 128 bit. And so instead of that, and the result, 128 bits, but I've written big, I wanted to hold big integers. So where there was 128, I just replaced by big unit. That's and the code remains the same. The code remains the same, just the same code. If you change this code and just replace by 128 and delete these libraries and go to the cargo toml and delete, the code runs. The code will still run. You delete this because you cannot have something that you're not using. If you have something that you're not using, then the code will not run. You'll be wondering why you have it there. So it's just the same thing. It's just the same code. The only thing I changed where there's U64, I've written big unit. Let's try to run this. Okay, so you can see it has given us a slightly bigger number. Let's try to increase it. Let's try to increase the number. Okay, I don't want to increase it too much because sometimes it may take long to run. That's not what I'm trying to. This one ran very fast and to give us a result. The result is here. Yeah, so that is how the code is, and you can change from the earlier code I gave is just the same code. This the only thing that now this one I'm using libraries that will handle for me larger integers. Now, so I want to show you how the code runs, how it functions to give us the result. I'd already begun that. I had already begun explaining, and that is what I just want to. So I've already explained this part. I've already explained that. Okay, understanding the Rust code. This Rust code, I've omitted the function, the main function, because that is the main function just putting our values, the base, the exponent, and the modulus. There's nothing much, and then it will be showing us what it will be, what it will run to give us, what the result, how the result will look like. Now, the function here, this function I've explained that the base is mutable, the exponent will be mutable, the modulus will be mutable and U64, and then the result will also be mutable, U64. And if the modulus is 1, it gives us the result that, and that's what I've just explained here. The first part here, I've just explained that. I've explained, and then I've said the base is mutable and the type 64. I've also explained that this means the exponent is mutable and is type 64, U64. The modulus is not mutable and is that. And then I also came to this part where I said, if the modulus, it begins with this. If the modulus is 1, it gives us the result as 0. That's what I've explained here. This is what this part means. If modulus is 1, return 0. It means if the modulus is 1, the function immediately returns 0. Note that any number modulo 1 will be 0. So modulo 1, we know what that means. We know what it means. If I have 2 mod 1, I'm asking myself, if 1 were to go here, what will be the remainder? So the remainder is 0. So any number mod 1 is 0. So the program is supposed to give us that very fast. Now, if the modulus is, okay, at this point, it says let mute. That is where the modulus is not 1. So when the modulus is not 1, then we begin. Let mute result. That means let the result be mutable. And we give it an initial value of 1. And then the base becomes the remainder of that base divided by the modulus. So this is what I've written here. I've said the result variable is initialized to 1, and the base is reduced modulus, and this is just to prevent overflow. That is, for instance, let me show you why this one is important. For instance, supposing I had 314 raised to 72 mod 70. While we were doing in class, we said in this case, we begin by reducing this number. So that is what is happening at this point. So the modulus divided by 70, write the remainder. So let me use a smaller number. Let me use 73. Let me use 73 raised to anything, 2314 mod 70. So in this case, we begin by reducing this modulus to 3, raised to 3. No, this base, we reduce this base mod 70. So this is what the program will be doing. Because if this is larger than the modulus, there will be overflow. So it begins by taking care of that. And that's what we are doing in class. We are beginning by reducing this base, first of all. So the program begins by doing that, and this is how it does. That the new base becomes the old base divided by modulus, the remainder of that. This is what it means. The remainder. This is what that means. Now, so out of that, we come to the while loop. The while loop begins with the exponent being greater than 0. If the exponent is greater than 0, then you enter inside. And the function says, the function enters a loop and continues as long as the exponent is greater than 0. So the only time you exit is when the exponent is 0. But once it's greater than 0, we continue with that. And this is where it begins. If the exponent divided by, this means the remainder, if the remainder of the exponent divided by 2 is 1. If the remainder, this is what it says, this is how I read this. If the remainder of exponent divided by 2 is 1, then the result should be the old result times the base divided by, so the remainder. The result should be the remainder of this divided by modulus. So that's the while loop. The while loop has a condition here. So the first condition, check if the exponent is greater than 0. If it's greater than 0, come to this part. Check. If this part is satisfied, then the result changes. So the only time we change the result is when this part is true. When this part is true, the result changes. If this part is not true, the result remains as above. It doesn't change. The exponent is still greater than 0, but if this part is not true, the result does not change. I'll be showing you an example. So the exponent is odd, multiply the current result by the base and take modulus. That is this part. The exponent, this part I already explained. The exponent becomes the old exponent divided by 2. This is what the question is saying. The exponent is divided by 2 using bitwise right shift. Bitwise right shift. So the exponent is divided by 2. The base is squared. So to get the base, you square the old base and divided by 2, write the remainder. This process continues until the exponent becomes 0, at which point the result contains the final value. Now, let me just now explain this example using the code. Just want to explain using the code. Now, I don't want to do it the way we've been doing it in class. Now, the first thing the thing will do, we let the result be 1. So let mute result 1. So the result is 1 and is mutable to be changing. Then we check the base, reduce it mod 27. This base is that 4 is greater than 27, reduce it. So when you reduce it, you have 7. So base is equal to the remainder of the base on division by modulus. That is 34 divided by 27, the remainder. The remainder is 7. Now, after that, you enter the main loop. And the main loop, you check if the exponent is greater than 0. In this case, our exponent is greater than 0. So we enter the main loop. And the main loop begins by checking, first of all, what is entering. What we are entering with is that the exponent is 35. The base is 7. We change the base at this point. The base is 7. Remember, this base will be changing. It will be mutable. And then the result we are entering with is 1. The initial result. The initial result is 1. Now, it begins. We are now inside the loop. Inside the loop, there's that thing we began with, the condition we began with was to check whether the exponent was odd. Let me just show you. Let me show you that part. This part is a part we are looking at. Is the exponent odd? In other words, on dividing the exponent by 2, do you get 1? That's where we begin with. That is where we are. That's the first part when you enter that main loop. Now, where is our exponent? The exponent is 35. On division of this exponent by 2, do you get 1? The answer is true. You get 1. So if it's 1, it says, then update the result. The result now is updated. How do you update the result? Let me just show you again. Let me show you. This is where it is. Let me just erase this. The code says, if the exponent on division by 0 gives you 1, then the result becomes the result above times base above, divided by mod. Then the remainder of that. The remainder of that is what the result is. Yes, so we've seen that our exponent on division by 2, the result, it gives us 1. That's true. So our result becomes this result times this base divided by the mod. Then we write the remainder. 1 result times base, the mod is 27. So this will be 7. 7 on division by 27. The remainder will be 7. So this is our new result. This is our new result. So we proceed with the next step. The next step, let me again show you the code, what the code says. Let me just go back to the code itself. Let's go back to the code itself. The code is here. The code is here. Now, what does it say? This is where we are. This is where we are. So what we are saying is, if the exponent on division by 2 is 1, update the result. We've updated. Then after updating, update the exponent. The new exponent becomes the old exponent divided by 2. Update the base. The new base becomes the old base times the old base divided by the modulus. The remainder of that is our new base. So we need to update. We've updated the result already. We are left to, we need to update these other 2, the exponent and the base. This is the formula. That is the formula for updating that. Let's just go back now and do it. Now that we know what we're supposed to be doing, we would move faster. We've updated the result. The result is 7. Update the exponent. Just take the exponent divided by 2. Our exponent is 35. Divided by 2, the result is 17. The result is 17. This is our new exponent. We will move with this to the next level. What about our new base? The old base times the old base divided by the modulus, the result of that. What is the old base? Here, we came with this base, 7. 7 was our old base. So 7 times 7 is 49. On division by 27, the remainder is 22. This is our new base. So we now want to move to the next step. What are we moving with? We are moving with the result that is 7. Our result is 7. We are also moving with a new exponent, which is 17. 17. We are also moving with a new base, which is 22, but the mod is still the same. The mod is not mutable. What was mutable was the base, the exponent, and the result. Now we come to the second iteration here. We are still inside that loop. We only get outside that loop once the exponent becomes 0. If before the exponent becomes 0, we remain in the loop. So we are still there. The second iteration, we have our exponent, which is 17 from this. We have the base again, the ones you are moving with. So the things you are moving with. Then we have the result. We go to the next, once you enter that loop, this is the first question. That's the first question. The question is the exponent odd? Is the exponent odd? In other words, is the remainder, when dividing the exponent by 2, 1? Our exponent is 17. It's true. It's true that when divided by 2, the result, the remainder is 1. So if that is the case, the code says update the result. What is our new result? Our new result is the older result times the base divided by the modulus. The remainder of that is our new result. So what is the new older result? Older result is here, 7. And then what is the base? 22. Yeah. And then that result, what you get here divided by 27, the remainder will be 19. So this is our new result. Then update the exponent by just dividing it by 2. And when you do that, you get 8. Update the base by just squaring it and dividing by the mod. When you square this and divide by the mod, the remainder is 27. 25. The exponent is not 0. The exponent is not 0. So we are still inside the loop. What are we going? We are going to the next step. And the next step, we are going with the exponent that is 8. We're also going with the base, which is 25. And we're also going with the result, which is what? The result is 19. So these are the things you are moving with until this exponent becomes 0. Okay, so these are the things you are moving with. The third iteration. The first question is the exponent odd? Is the exponent odd? This time it's not. The exponent is not odd. It's false. So if it's false, we don't update the result. We don't update the result. The result remains as it is. But we update the exponent by dividing by 2. We also update the base by squaring it and dividing by the modulus. The remainder is 4. So the result we don't update because the exponent was not odd. We got the fourth iteration. What are you going with? We are going with the same result, which is 19. We are going with the exponent new, which is 4, and the base, which is also 4. The exponent 4 and the base 4. And the question is the exponent odd? Again, the answer is it's not. The exponent is not odd, and therefore we don't update the result. What we update is the exponent by dividing by 2, and you get 2. And then the base, update it by squaring it, and then divided by the modulus, and the remainder is 16. We go to the fifth iteration. Fifth iteration, what are we going with? The same result. The result has not changed twice. And we have updated the exponent is 2. We've also updated the base, which is 16. So you can see the base is changing. Now, what the things where we are changing the result is where we had, when we wrote our power. Remember we had a raised to k. When we wrote this k in binary form, the only point where we are changing the result is where the binary number was 1. And where it was 0, 0, 0, and so on, we are not changing. That is the way we are not changing. And you'll discover these bases. These bases are the answers we are getting. We are getting, for instance, when you took 7 raised to 1, the answer you got is what we are calling the base. When you took 7 raised to 2, the answer you got is the base again. When you take 7 raised to 4, the answer you get is the base. So this base is changing. The bases are changing. When you look at this example we had done it earlier manually. You'll compare with this and see the values you're getting for the bases are the values you are getting when you took those numbers raised to 7 raised to 2, 7 raised to 3, and so on. Now, so let's go to the next, this 5th iteration, 6th. What are you going here with? We are coming here with the result, which is 19. We are coming here with the new exponent, which is 1. We are coming here with the new base, which is 13. Is the exponent odd? The result, the answer is it's odd. So if it's odd, then change the result. The result becomes the old result, which is 19, times the base, which is 13, then divided by the modulus, the remainder is 4. Then update the exponent by dividing by 2. The exponent is 1 divided by 2. When you divide 1 by 2, you get 0. The exponent is now 0. We are just about to exit. And then the base squared. What is the base? 13 times 13 divided by 27, the remainder is 7. So we exit the loop. The exponent is now 0. We exit the loop. So when you exit the loop, what is the result? The result is what is here. What is here is the result. What was the last result we got was 4. So this is how this code works. You will just compare these workings with the ones we did above, and you discover that what it does, like the one we did, we converted the exponent to binary. So where we had 1, 1, 0, 0, where there's 1, 1, at this time you get that the exponent will be odd. The exponent will be odd. The remainder will be 1, that 1. So in that case, the result changes. You change the result. But where there's a 0, the exponent was always even. The exponent will be even, and therefore the result does not change, and so on. Thank you. I think next time we shall again look at it. It's good to know how the code functions so that you can easily write it. Thank you.